The next part of thermodynamics, we're looking at bond energy, and this is actually part of Chapter 8. So we've looked at how energy flows into and out of a chemical reaction. Now we're going to take a look at where this energy is stored in the substances. And that's what we're going to look at, is the energy that's stored in the bonds. Bond energy is the amount of energy that's involved in forming bonds or in breaking bonds, and we're looking at covalent compounds when we're looking at bond energy. When bonds are formed, we have an exothermic process going on. Energy is given off. So generally bonds are formed when we have products being formed, and so energy is going to be given off during that part of the reaction. When bonds are broken, usually that happens to the reactants, and this tends to be an endothermic process. So it requires energy to break those bonds. Okay, bond energy for a reaction can be used to approximate the heat of a reaction, and we can use this by doing an algebraic process, looking at the energy involved in breaking all the bonds of the reactants and forming all the bonds of the products. If the reactants and products are gases, that's when we're going to get our bond energy. So if we're looking at a reaction that involves liquids or solids, it's going to be even a more distant approximation rather than a fairly exact approximation for the heat of the reaction if we're looking at bond energies, positive and negative. If bonds are weak, it doesn't take much energy. These molecules tend to be unstable. In compounds that have strong bonds, that involves a high amount of energy, and these tend to be very stable compounds. The reaction we're going to use to approximate the heat of the reaction is the sum of all those bonds broken minus the sum of all the bonds that are formed. So, both in the case of the heat of the reaction when we're looking at heats of formation, and in this case where we're looking at sum of bond energies broken and formed, it's going to be alphabetical. Heat of reaction, looking at heats of formation, it's products minus reactants. P comes before R in the alphabet. When we're looking at bond energies, bonds broken minus bonds formed, B for broken comes before F formed in the alphabet. So how do we figure out the heat of a reaction approximation if we're using bond energies? Well, the first thing to do, we need to write out the reaction using Lewis structures. The reason we're going to use those Lewis structures is to show us where the bonds are, what bonds are broken, what bonds are formed, and what bonds we can ignore because they don't change. So we're going to take a look at this reaction. Back to our favorite, hydrogen plus oxygen gives us water. So if we draw it out in terms of a Lewis structure, it'll look like this. There's a single bond between the two hydrogens, double bond between the oxygens, two OH bonds in the water. So there is our chemical reaction written out in Lewis structure format as we did in symbols above. Now what we need to do is there is a chart of bond energies in Chapter 8, and we're going to use that and figure out what is the bond energy for hydrogen-hydrogen bonds, for oxygen-oxygen double bonds, and for hydrogen-oxygen single bonds. And we're going to use that to figure out an approximate heat of reaction. So bonds broken. So here is our hydrogen being broken. Here is our oxygen being broken. Since we have two hydrogen-oxygen bonds, we need the 2 times that value, which is the hydrogen-oxygen bond. Bond energies in the table are listed as all positive because you assign the value based on the sum of the equation. So we end up with negative 255 kilojoules for creating 1 mole of water. Now if we compare that to what we found for heat of formation of water in the table, we'll find it's not quite the same. Again, this is an approximation. If we look up heat of formation of water in the table, what we'll find is this. So the heat of formation when water is a liquid, we get negative 286 kilojoules. If we're looking for heat of formation for water as a gas, we get negative 242 kilojoules. So if we look and see what we ended up with as an approximation, 255 is in between those two because we're dealing with assuming it's a gas, but it's not necessarily actually a gas. We're looking at bonds, hydrogen-hydrogen bonds, oxygen-oxygen double bonds, hydrogen-oxygen bonds in all sorts of compounds. So again, it is an approximation, not an exact value. If we look at this next example, again, thing to do would be to draw out the Lewis structure. So methane is carbon attached to 4 hydrogens. I have two oxygens. Oxygens are double bonded. I'm going to form carbon dioxide. Oxygen is double bonded to carbon, and I have two waters. So there is my reaction. Now I'm going to put the values in so that I can get heat of reaction approximated by the heats of formation. And so the numbers are going to look like this. 4, because there are 4 hydrogen-carbon bonds, and hydrogen-carbon bond is 413 kilojoules. I have 2 oxygen-oxygen double bonds, and then I'm going to subtract the bonds broken. I have 2 carbon-oxygen double bonds, and 2 times 2 or 4 hydrogen-oxygen bonds. And what I get is negative 824 kilojoules. Again, bond energy dealt with covalent compounds. What we're going to look at now is lattice energy. Lattice energy essentially deals with crystalline solids, usually ionic. Again, lattice energy is in Chapter 8, so we're going to continue with a little bit more of chemical reaction energies in a slightly different format. Lattice energy is defined as the change in energy when gaseous ions, not gaseous atoms, gaseous ions, are close packed to form an ionic solid. When the solid is formed, energy is given off, so it tends to be an exothermic process as the ions condense. If we want to look at an example, we're going to make lithium fluoride. It's an ionic solid. We're going to start with solid metallic lithium and gaseous fluorine, which is a diatomic gas. First thing we have to do is break things apart. So we're going to sublime the lithium. So we're going to take lithium solid to lithium gas. And we're going to look up the heat of sublimation. We get that value. For 1 mole of lithium solid to lithium gas, we get 161 kilojoules. It's endothermic. Energy needs to be put into the system for that to happen. Okay, once I have all these gaseous lithium atoms, I need to ionize them. So I'm ripping electrons off, 1 electron per atom. Ionization energies have been determined. Ionization energy is 520 kilojoules for 1 mole. Again, it's an endothermic process. I need to put energy into the system to rip those electrons off. Now my lithium, half of the atom is half the molecule is all set to go. It's positive lithium ions in the gaseous form. Now we take care of the fluorine. Fluorine's diatomic, so first thing I have to do is separate those 2 fluorine atoms. So I'm going to look at a bond energy. I'm going to take half a mole of fluorine, and I end up with fluorine atoms. I don't end up with 2, I end up with 1. So half a mole of fluorine molecules gives me 1 mole of fluorine atoms. The bond energy is per mole, so I'm going to take 1/2 times the bond energy of fluorine molecules, which is 154 kilojoules. Again, energy is required to break it apart. Now I have fluorine atoms, they're gaseous atoms. Now I need to make them ions. To ionize the fluorine atoms, I have to add electrons. So this is an electron affinity. Again, it gives off energy. Fluorine atoms are less stable than fluorine ions. So it's an endothermic process when I'm ripping things apart. It's an exothermic process when I'm ionizing the fluorine. Negative 328 kilojoules for 1 mole of atoms. Okay, now I'm going to take the positive lithium ions. I'm going to take the negative fluoride ions. They're going to combine, and when these ions combine to form the solid compound, this energy is known as the lattice energy. I can look up the lattice energy, just like I can look up bond energy and sublimation energy, and I get 1,047 kilojoules. It is very exothermic energy is given off. So if I want to figure out what is the total amount of energy in lithium plus half a mole of fluorine going to lithium fluoride, I'm simply going to add up all these 5 steps and find out what is the total amount of energy involved in going from the elements to the ionic compound. So there's my overall reaction, there's the overall energy. So heat of the reaction is exothermic, it's negative 617 kilojoules per mole. Usually we're asked to either find the energy of the overall reaction, as we did in this example, or you're given steps 1, 2, 3, 4, and you're given the overall heat of the reaction, which is part 6, and you're asked to work backwards and find the lattice energy, which is essentially the value in step 5 that we did.